Okay, so we already talked about electrons behaving like tiny magnets. So they have this little bit of a spin, and that these magnets can be attracted to magnetic field. So an atom that has unpaired electrons tends to be magnetic in general. So a paramagnetic substance is one that is weakly attracted to a magnetic field, and it is because it has unpaired electrons. So in some orbital, it only has one electron. A diamagnetic substance then is not attracted by a magnetic field. It's not magnetic because it only has paired electrons. Okay, the periodic table. So the discovery of new chemical elements, we know, has been going on since ancient times. Of course, the Greeks and the Romans had gold, they had silver, they had copper, a number of different a number of different elements. And then there are some elements that are radioactive, and we really don't know about them except because of technology. And so in the 1800s, it turned out that more and more elements were being discovered. And so in the early 1800s, that number jumped from 31 up to 63. As the number increased, the scientists began to figure out ways to classify them. For example, Mendeleev wanted to be able to help his students remember all the elements, and so he came up with this classification scheme. And Meyer also did something very similar. Mendeleev was Russian, Meyer was a British scientist. So they both noted that there are similar chemical and physical properties that recur as you go across the periodic table. So in other words, as you start over again, those properties start over again. And so everything in group 1A, for example, act very similar to other things in group 1A. So Mendeleev, in fact, was so insistent that elements of similar characteristics be listed in the same family, he was forced to leave several blanks in his periodic table. He said, no, there's some element out there that should fit there. So, for example, gallium and germanium were unknown at the time, and he left blanks where those should be. And he was able to predict that they existed and, in fact, predict what some of their properties would be like. And then, in fact, when they were discovered, they found that these were very close to what Mendeleev had predicted. So periodic law says that when the elements are arranged by atomic number, their physical and chemical properties vary periodically. In other words, they repeat themselves. We're going to look at three periodic properties: atomic radius, ionization energy, and electron affinity. So before we do that, let's look at the periodic table first. And notice that the periods go across the periodic table. And so you can see numbered on the left, 1 through 7. So period 1 is hydrogen and helium. Period 2 starts with lithium and goes through neon. Period 3 is sodium through argon, etc. So those are the periods. And then the groups go up and down. And so there's two different numbering systems for the groups. You can see that the more modern numbers are 1 through 18, and those are on the top here. That's why I put this periodic table. There's actually a different numbering system that uses A's and B's, either with a Roman numeral or with an Arabic number. So you can see 1A, 2A, and then skipping over those yellow transition metals are 3A, 4A, 5A, 6A, 7A, 8A. And so we have the A's and the B's, and and then the B's are the transition metals, so 3B, 4B. It's kind of a weird numbering system, which I guess is why they went 1 through 18. But I like the A's and B's because the A's are all the main group elements, which are the S's and the P's, and then the D's are the transition metals, which always come a little bit behind. So sometimes the A's and B's are a little bit helpful, as we'll see. The A groups actually are the same as the valence electron. So 1A has one valence electron, 2A has 2 valence, 3A has 3, and so forth. And then also you can see that the F electrons, those lanthanum and actinide series, actually fit in. You can see that they come after the 6S and the 7S. All right, so let's look at these periodic properties. Atomic radius. Within each group, if you go down a column, you can probably imagine that atoms get bigger and bigger. So the radius is just from the center of the atom to the outer electron. How big is the radius? And so it would get bigger and bigger the more shells that you add. So if you're in the 7th shell, it should be much bigger than the first shell. And so atomic radius gets bigger as you go down a column. Within a period, you might assume that it should be getting bigger as you go from left to right because you're adding more electrons. Actually, this isn't true. Then your second thought might be, well, because you're adding them all to the same shell, then maybe they all should be the same size because as you add them, you're adding them to the same distance out, so they should all be the same size. But in fact, the size decreases as you go from left to right. So let's look at what makes these two trends true. So, of course, the first factor is the principal quantum number. So like I said a minute ago, the bigger n is, the larger the orbital is, the larger the shell is, and so the larger the radius is. So that's going down a column. But what's happening when you go across is something called the effective nuclear charge. And that's just the positive charge and electron experiences from the nucleus. So what it is basically is you take the number of protons and you subtract the number of electrons that are in all the shells below it, and you see how many positive charges are pulling on those electrons. So let's look at the next slide. So you can see that as you go across the period, they actually get smaller. So what do I mean by that? So if you look at period 2, lithium has 3 protons and 3 electrons. Well, the only outer shell electrons is that one, the 2s1 electron. So it's got 3 protons and it has 2 shielding electrons, the ones in period 1. So if you subtract that, you get a +1 charge. So that electron in the second period is feeling a +1 charge. When you get to beryllium, remember that it has 4 protons in the nucleus. It also has 2 shielding electrons, those in period 1, and it has 2 period 2 electrons. But if you always subtract the shielding electrons, so if it has 4 protons minus those 2 shielding electrons, it actually has a +2 charge. So it's pulling a little bit harder on those outer electrons. Boron has a +3 charge. We keep adding more and more protons, but the number of shielding electrons between the nucleus and the outer electrons doesn't change across a row, and so the positive charge pulls harder and harder on the electrons. So the same thing happens in period 3. Sodium really only has 1 electron in the third shell. So there are 2 electrons in the second shell and 8 electrons in the 2 electrons in the first shell, 8 electrons in the second shell. So there's a total of 10 shielding electrons all across period 3, 10 shielding electrons. Sodium then, with 11 protons and 10 shielding electrons, has a +1 charge, effective charge. Magnesium also has 10 shielding electrons, but it has a +12, so it has a net +2 effective charge. And so again, because all across period 3 those shielding electrons are 10, but we keep adding more and more protons, they're pulling harder on the outer electrons, pulling them in closer and closer. So that explains the trend going to the right. All right, so what about ionization energy? Well, the first ionization energy of an atom is defined as the amount of energy needed to remove the highest energy electron from the neutral. So the last electron that you put in, how hard is it to pull it away? So for example, a lithium atom, the ionization is illustrated by this. So we have the neutral lithium with 3 electrons, and then on the right hand side we have lithium with 2 electrons and 1 electron removed. How much energy was required to do that? 520 kilojoules. So what's the trend on the period? So there's a general trend that ionization energies increase as you go across a period. It's just going to be harder and harder to pull those electrons away, and that sort of goes hand in hand with that effective charge. So it's those protons, the effective nuclear charge, are pulling harder on those electrons, pulling them in closer, so it's going to be harder and harder to pull one electron away from that. So the ionization energy increases as you go from left to right across the periodic table. So again, that's why it's, like I just said, it's harder to remove an electron that's closer to the nucleus. And for the same reason, as you go down a column, ionization energies are going to decrease as you go down a column because those electrons are farther and farther away from the nucleus, so it's going to be easier and easier to pull them away. So this shows kind of your general trend. Of course, there's differences within each period, but overall, as you go down a column, so if you look at helium, neon, argon, krypton, you can see that the ionization energy goes down because as the molecule gets bigger and bigger, it's easier and easier to pull those electrons away. The same trend happens with lithium, sodium, potassium. It gets easier as you go down a column. But then if you go across a row, across a period, so like from lithium to neon, you can see that although there are a few little glitches in there, in general, it's harder to pull an electron away from neon and fluorine and oxygen and nitrogen than it is from lithium. So as you go from left to right, it gets harder and the ionization energies increase. You can also remove more than one electron. So you can have what's called the second ionization energy, which is how much energy is it required to remove a second electron. Now, how easy it is will really depend on the element a whole lot more in this case. So let's look at this table. You can see helium, of course hydrogen only has one electron. Helium is much harder to pull the second electron away, although helium is very hard regardless. Now lithium, it's pretty easy to pull that first electron away, but notice that once you do, it's got a full shell underneath and it really doesn't want to pull, so it's like extremely much harder to pull a second electron away from lithium. Now beryllium, which has 2 electrons in its outer shell, it's not so bad. So the first one is fairly easy, 899, and then to pull the second one is a little bit harder, but not that much harder, and then you can see the huge jump to 14,000 if you try to get those inner shell electrons. The second ionization energy is not as critical to understand. All right, and then related to electron ionization energy is something called electron affinity. It's almost the opposite. The electron affinity is how much energy, what's the energy change for adding an electron to a neutral atom, so to make a negative ion. So it's the opposite of pulling an electron away. So for chlorine, you can see that adding an electron gives you a negative charge, and you fill up that shell. So in fact, the electron affinity is negative 349. That means that it gives off a fair amount of energy for this process to happen. The more negative the electron affinity, the more stable the negative ion is, which is, the better, the more likely that atom will gain an electron. So broadly, the trend goes from lower left to upper right. So the affinities become more and more negative. In fact, it becomes more and more possible to add an electron as you go from the lower left-hand corner. So as you increase, it's a little bit easier to add an electron, and as you go from left to right across the periodic table, it's easier to add an electron. So fluorine would be the highest, have the highest electron affinity of any element on the periodic table. Helium, neon, and argon don't count in that trend because they don't want any more electrons. So the next table will give us some electron affinities. And you can see that fluorine and chlorine have some of the highest electron affinities, the most negative. That means they like getting electrons the most. And you can see down here at the bottom, cesium and tellurium and indium are very low. Okay, so let's just talk a little bit about the physical and chemical properties of the different elements on the periodic table. So there are variations of metallic and non-metallic character and also acid-base behavior. So we're just going to take a little survey of the periodic. So if we look at group 1A, which are the alkali metals, they have the largest atomic radii, as we just saw. They are very reactive. They react violently with water. They react violently with halogens. They ionize to a +1 charge. They're very metallic. They oxidize in air. They conduct electricity. They're very reactive. They don't exist in nature. And they're very soft metals. And you can read some of these other things. So sodium is found in a wide variety of compounds. Potassium is used in fertilizers, soaps, explosives. Lithium, as you probably already know, is used in batteries. Group 2A are the alkaline earth metals. They will ionize to a +2 ion. They also react very much with water to form hydrogen gas, not quite as violently as the alkali metals. They have a closed S shell configuration, so they're all paired electrons and they won't be magnetic. They're metallic also, so shiny, and they conduct electricity, all those kind of things. They are also too reactive to exist in their elemental form for very long. And you can read some of these things here. Calcium, of course, is found in seashells and limestone and in your bones. Magnesium is also important for nutrition and can also be found in your bones and in milk of magnesia. Barium used for fireworks, rat poison, medical x-rays. Beryllium also used in x-ray tubes. Strontium is often used in fireworks because it has a bright red color. Transition metals, there are a number of transition metals that you're familiar with, and many of them have been around for centuries and millennium. They often have several oxidation states, which means they can be at more than one charge. They can have more than one charge, like iron can be +2 or +3. They're metallic, shiny, hard, dense, good conductors, all the things that metals are good at. They are reactive with acids. You can see here some of the variety, and these are some things you probably already know about. Titanium, being very dense and strong but lightweight, is often used as a joint replacement or also in building aircraft. Copper, of course, is used in wiring and in pipes. Nickel, used in coins. Iron is used in building materials. Can be used as catalyst in manufacturing. Iron is usually the red pigment. Iron oxide is the red pigment in red paint. Also, of course, you know it's important in your blood nutrition. Silver and gold and platinum are often made into jewelry. Palladium, is often used as a catalyst in many reactions, and you got some of the other elements here. So lots of transition metals. Group 3A are also metals, except for boron. Boron is a metalloid, and they generally are a +3 charge, although some of the lower ones, like indium and tellurium, can also be a +1. Just a few things there about some of the other elements. Aluminum is the most abundant metal on Earth. It's very strong, light, and malleable, meaning it can be made into sheets. As I'm sure you know, used for foil. It can be used in a catalyst, used as a catalyst, and it's also used in fireworks and rocket fuels. Boron is not as shiny because it's a metalloid, and it's in many compounds. It's especially used in making glassware. Borosilicate glass is what we use in the lab because it's heat resistant. Gallium is a very low melting solid. It could actually melt in your hands, and it's used in LED lighting, and indium is sometimes used to make mirrors. Group 4A form the most covalent compounds. These include carbon and silicon, and so they're actually, so these are the least ionic, and their oxidation numbers can vary quite a bit, although tin and lead can be ionic, but the carbon, silicon, and germanium are not. So as you, I'm sure, know, carbon is found in diamonds, graphite, which is what's used in pencils, coal. It's the most important element for life because all bodily molecules have carbon in it, just about. Most biological compounds contain carbon. Silicon is also one of the most abundant elements on Earth. Silicon oxide is quartz, and so it's found in rocks and minerals and maybe different structures of it, but all sand. Silicon is also used in semiconductor computer chips. And then just a little bit about germanium is often also used as semiconductor and transistors. And lead is still used, although it used to be used for pipes. PB stands for plumbum, which, you know, you see the root for plumber in there, although they're not used for pipes anymore because of their hazardous. But they're still used in car batteries and for shielding you from X-rays. Group 5A is the nitrogen group, and they tend to form negative ions, mostly -1, mostly -3 ions, but in compounds they can form -1 and -2 ions. This one has quite a range from nonmetals to metals. So we know nitrogen is a nonmetal, phosphorus is a nonmetal, arsenic is a metalloid, and then tin and bismuth are both metals. Just a few things. Of course, nitrogen we know is an inert gas as an element, and it's found in a wide variety of compounds. Ammonia. It's important for many life functions. It's found in your DNA and proteins, etc. Phosphorus, it's also used in fertilizers. Phosphorus is also used for making matches, also used as a fertilizer in fireworks, etc. Arsenic, besides being notorious as a poison, it's also used in car batteries and as a semiconductor for computers and things like that. Group 6A is the oxygen group. They tend to form a -2 ion. Although other oxidation states are possible. They react vigorously with alkali and alkaline earth metals. They are nonmetals for the most part, except for polonium, which is not very common. We know that oxygen and sulfur are both essential for life. Oxygen supports combustion necessary for all life except for anaerobic bacteria. So if we didn't have oxygen, we wouldn't have life, obviously. It's in hundreds and thousands of compounds. Silicon is also used to make rubber stronger, but it's found in your body a little bit and in other compounds. And then selenium is used in semiconductors and also used in photocopying, in dandruff shampoo, and in photocells. Okay, the halogens, which are group 7A, form monoanion, so -1 anion. They have high electron affinity. When they're in their natural state, they form diatomic gases. And they're all very reactive nonmetals. So we're finally into the column that has mostly nonmetals. Chlorine you can see as a gas at room temperature. It's kind of green. It's used in bleach and to keep swimming pools clean, or also to bleach wood pulp for making paper. Of course, it's found in salt, so it's everywhere. Bromine is the only nonmetallic liquid at room temperature, and it's used in photographic compounds and petroleum production. And iodine is a solid, and it's important in thyroid function in your body. That's why we have iodized salt, because you need to have iodine in your diet. And a radioactive isotope of iodine is used to treat thyroid cancer. And then finally, the noble gases are very unreactive. Xenon might react a little bit. The others not at all. They are all monoatomic gases, so they don't interact with any other elements. They're all colorless, odorless, tasteless. They have a closed electron shell. Obviously, you know helium is used in balloons, and you may not know, in deep sea diving. It's not flammable, so that's why hydrogen used to be used in balloons until the Hindenburg exploded. Helium is found in the spectrogram of the sun, so mainly in the sun there's only helium and hydrogen. As you, I'm sure, also know, neon is used for lighting different elements. Different elements like argon and mercury are added to make the different colors. So standard neon a true neon light would be orange, and then other colors would be from other elements. And you can see there, xenon is used for lighting, lasers, and phototubes. Okay, so that's chapter 8, and what should you be able to do in this chapter? You should be able to apply Pauli's exclusion principle, which says that no two electrons can have the same 4 quantum numbers. You should be able to determine the orbital diagram and electron configuration for any atom using the Aufbau principle.